Yes? Oh, I'm on. All right, everybody. My name is Danica Fine. I am a developer advocate at Confluent. So I do a lot of work with Apache Kafka, event-driven systems. Beyond that, the only other thing that you really need to know about me is that I like houseplants. And here's a little bit of proof. These are all my houseplants, or not all of them. This is a subset of my houseplants. I have about 3 or 4 dozen, actually, scattered around my house. That's entirely too many, in case you're wondering, but also not enough at the same time. I'm going to keep going. How many of you have houseplants? Oh my God, I love this. That's so great. All right, so this is really going to resonate with you. You're going to love this. You know also probably how much work it is to take care of houseplants, depending on how many you have, what kinds you have, whatever. For me, what that meant was doing the rounds every morning, checking on the plants. During the pandemic, this is the thing I did every day, all right? I needed something to help me wake up in the morning, exist. So I would check on the plants, see who needed to be watered, which ones needed to be rotated, get more sunlight, what needed to be fertilized. That's a lot of work with 40 plants, right? And then at the end of the day, I would check them again because why not? It takes a lot of time. And when the pandemic started winding down and I had to leave my house, this became a problem, right? It wasn't just a fun thing I could spend my time doing. I now had to work that into my regular schedule. And I was a bad plant mom. Okay, I forgot to water this guy in the morning. I came back, very dramatic. It's not supposed to look like that. It ended up being fine, but I felt bad, right? This was only going to get worse. I was going to go to conferences. I was going to leave. I wouldn't be home the entire time. And so something had to be done, right? So I asked myself, is there a better way? I needed some way to monitor my houseplants and at least remember that I had to care about them that day. And, of course there's a better way, right? This is kind of a stupid question. There's definitely pre-made solutions out there. I can go to the store, I can buy something to monitor my houseplants, but that wouldn't make a good story. We don't care about that. Many of you are engineers, you're developers, or at the very least, you're a creative person or curious, so you are here. So this is a bad question. This is the question we really care about, right? As an engineer, you want to build the interesting solution, the elegant solution, all right? Not just the easiest way out, right? So I spent a couple years building out streaming data pipelines with Kafka professionally in industry. And when I became a developer advocate, I decided that the projects that I built, I wanted to build them for me. I didn't want to just build a toy project for fun. I wanted to build something that I actually needed. So this was it, right? I had a real problem that could be solved with Apache Kafka in my house, and add into that I really wanted to get into IoT. I wanted to build something with a Raspberry Pi. So this is the perfect storm, the best possible opportunity for me to do that, to combine Kafka with my love of houseplants and also check a couple boxes and do a hardware project. It was great. That was reason enough to do this, and my boss said yes, so I did it. Let's talk design. All right. Nice diagram. The bottom line is that I needed something to monitor my plants, right? At the very least, let me know when they need to be watered, okay? Let's not get into the whole problem of actually watering the plants. I don't have reservoirs all throughout my house to water these plants. I'm so sorry to disappoint you. But I at least needed to be reminded every day to check on the plants that actually needed to be cared for. So the system I wanted was pretty simple, right? I'd have these soil moisture sensors in the plants, collecting readings regularly, and producing that in the Kafka. I just toss it in there, right? But that information on its own probably wouldn't be good enough, right? Every plant is different. They all have different requirements. And so I'd need some extra information, some metadata to help me actually act on those readings and, tell me if they need to be watered, right? So I'd throw that information also into Kafka and just leave it there. And mix it all up, use some stream processing, and in the end, I wanted to spit out some sort of alert, ideally on my phone. All right, that sounds pretty good. I'm satisfied. How many of you have ever heard of Kafka? You've heard of it. How many of you use it in production? Not as many. All right, so was anybody counting how many times I said Kafka at the beginning? I tried to limit it, but surprise, we're using Kafka. So it's a huge part of my project. It's honestly the backbone of it. So I just want to make sure and take some time and make sure we're all on the same page. We understand what Kafka is, how to use it. Kafka's complicated. There's a lot that goes in there. I kind of boiled it down into the most concise definition possible. It's a distributed event streaming platform. 3 words in there that really matter, but there's a lot to unpack. So let's do that. First and foremost, Kafka is a streaming platform, all right? I'm not talking Netflix, although Netflix does use a lot of Kafka. So if you're interested in that, check out their talks. They've got a million of them. But you may have noticed over the last few years, last decade or so, we've been undergoing a paradigm shift in how we deal with our data, how we handle it, how we process it. We're moving away from batch-focused processes, right, where we're waiting minutes, seconds, days, to batch the data and then process over that. And we're moving to real-time systems, right, where as the data is being produced, as we're generating that, we are then processing it. We're moving it around. We're letting other systems react to that information as it's being created. And this move to stream processing, first of all, there's many technologies that you can use to achieve stream processing. But depending on which one you use, like you can actually increase the overall accuracy of your data. You're going to have a more reactive system, obviously. And in the case of using Apache Kafka, you get a lot of other cool things for free. You're going to increase the resiliency of your overall system, decoupling a lot of areas of your architecture. And it's great. I think it's really cool. So Kafka is a platform that allows you to achieve stream processing. It serves also as a messaging system, a persistent storage layer, and also you can get some cool processing in there as well. So it is a streaming platform. But it's also an event platform. And if you take nothing else away from this talk, and you're looking to use Kafka, this should be it, all right? In order to be successful with Apache Kafka, you need to start thinking in events, all right? And this isn't me asking you to rewire your brains, I promise. As humans, as users, as programmers, you already think in and process in events, I promise, okay? You submit information online, web forms, you look at application logs to debug, you react to notifications on your phone. All of those things are events. You just gotta think about it, right? So those are all examples of events, but what is an event, really? Well, it's a piece of information, ideally the smallest amount without too much excess, that fully describes something that has happened. That's it, all right? Just something's happened. Let's record it. So what do you need to know to describe that something has happened? You need to know a timestamp, you know, when it happened. That's pretty critical. You need to know who or what was involved, and then any other supporting details, right? So in the context of this plant system that I was building, we're going to be collecting soil moisture readings, right? So as an example, we could say yesterday at 2:30 p.m., my plant, pictured here, had a soil moisture reading of 19%, right? So we have the timestamp, the critical component, yesterday at 2:30 p.m. We have the subject, that plant, and the supporting detail. It had a moisture reading of 19%. Cool. Another really critical thing about events is that they are meant to be immutable. I'm so sorry if that doesn't vibe with you, but that is how it is. We've described things that have already happened. We can't go back and change them. We're not going to, all right? Once that event has occurred, it is there, all right? That plant had a moisture reading of 19% yesterday. If I want to change that, well, I can't really change that, but what I could do is I could water the plant today, and then at some point in the near future, it would have a soil moisture reading of, say, 70%, right? And we would write that event, okay? I didn't erase the fact that we had a 19% reading yesterday. I've simply added another event to that timeline of events, that stream of data that describes the moisture state of that plant over time, all right? So that's what you kind of have to think about when you start working with events. So based on what you just learned, you know, Kafka is a streaming system. It helps you move information in real time pretty efficiently. And the fact that we are communicating immutable facts across that system. First of all, that's a great thing because when you are dealing with immutability, it makes it a lot easier to copy data around, move it around, and you're also ensuring the integrity of that data for downstream systems. So it's pretty powerful. But how does Kafka actually achieve this? And this is where we get into that third word, distributed. It is a distributed system, for better or for worse, you know, whatever that comes with. When you're dealing with storage in Kafka, the primary unit of storage is the Kafka topic. And this typically contains, you know, a single data set of events. All right, so you write events into Kafka as key value pairs, and that key is really critical. We need to know where to sort of store that event in Kafka. And you do this using a separate client called a Kafka producer. You can have as many producers as you want, writing to as many Kafka topics as you want. From there, you read the data out of Kafka using another client called a consumer. You can have as many of them as you want, reading from as many topics as you want. There are a lot of cool features about consumers. The first thing is that by default, they keep track of where they've left off. When they're consuming from a Kafka topic, it's very beneficial to know what was the last event that I read, right? The last one that I successfully processed. And every event in a Kafka topic has a unique identifier and offset that it can be used to identify where that consumer has left off. So they're constantly committing that back to the the cluster, so we know where we left off. Consumers can work together as part of a consumer group, and in doing so, they're able to read from the same Kafka topic and parallelize the processing of those events from the topic, which is pretty cool, because we want to achieve parallelization, right? But they're also free to read independently. We can have a bunch of consumers reading from the same Kafka topic and getting the exact same events one by one from that topic. And that's a really important thing, actually. If you're learning Kafka for the first time, it's easy to compare it to other sort of similar technologies, maybe like messaging queues, and I don't want you to go down that path, all right? A Kafka topic is not a queue. When you consume the events from a topic, they don't go anywhere, all right? It's more akin to a log, like a log file, all right? An application log. When you look at that file, you're debugging line by line. What happens to those log lines? Absolutely nothing. They are there. They are durably written in that log file, ignoring when it rolls, right? But they're durably written into that log file until it's cleaned up, right? And during that time, anybody can come along, your colleague can come in and read line by line through that log file to build up that same state of application in their mind as well. And also, as an aside, every line in a log file is an event, okay? There's a timestamp, tells you something that has happened to a particular area of the system. So the events, they're everywhere. They're innocuous, okay? So these events, they don't go anywhere. They're in the Kafka topic, and that's pretty cool for flexibility. The flexibility. Other areas of the system can tap into the same information. That's pretty cool. Consumers are completely decoupled from producers. They don't care about each other, and that's great, right? We want to maintain that decoupled sort of system. Producers don't care who's reading from their topic that they produce to. Consumers don't care where the data came from. There's a whole governance aspect in there, but at the default level, at the high level, they don't care about each other. Kafka topics are actually broken down further into something called partitions, and these partitions are themselves the immutable append-only logs where the data is actually stored, okay? And Kafka is a distributed system, so these partitions are stored across the cluster, and this provides better resilience and facilitates replication of this data. I'm going to illustrate that here. The nodes of a Kafka cluster are called brokers, and you can have them running anywhere. They can be on bare metal, VMs, containers in the cloud, wherever. It really doesn't matter. This is a simple cluster with 3 brokers. There's 3 topics spread across it, and they have some number of partitions that are split up. This is an example of how the partitions might be distributed. Results may vary. But why should we bother putting partitions on different nodes? Why do we care? The biggest reason is when it comes to the actual processing of the data later on. As I mentioned before, the consumers have the ability to work together to process data. And what that means is that they're given a set of partitions to effectively own and consume from when they're working together. And so in this case, if we had 3 consumers consuming from topic 1, those 3 partitions exist across this cluster on different brokers, and so those consumers aren't connecting to the same broker to request that data, right? We're reducing the network load for that single broker, and we're spreading it across multiple, okay? So those consumers are going to be able to get that information a little bit faster than if they're all competing for the same resources. So what that means is that you want your data to be spread as evenly as possible across those partitions and across your cluster. And that's great, but what if a broker goes down? You have to consider that, right? I mean, this is clearly not ideal. We've lost almost a third of the data, but Kafka does take this into consideration with replication, which is a configurable parameter that defines how many copies of a given partition will exist across the cluster. So in this case, we have our 3 brokers. We're looking at a single topic, though, and this topic has replication enabled with 3 replicas. So with replication enabled, when we write data to a partition, say partition 0, it's written to what's known as the lead partition on broker 0. And then synchronously, we copy that data over to the follower partitions that exist on other brokers throughout the cluster. So by the time we come back and say that event was written, we know it exists in 3 places across the cluster so that if broker 0 goes down, we still have 2 copies of that data elsewhere. And we can go ahead and promote one of those follower replicas to be a lead replica, and our consumers and producers can continue doing what they were doing. All right? I know that was a bit of a technical aside, but all that to say is that Kafka is pretty good at storing your data, your immutable events, in a reliable, persistent, distributed way for fast consumption. It sounds like a sales pitch. Kafka's great. I love it. And they can serve that information up pretty quickly and efficiently. And you also have some cool data processing within the ecosystem as well. So yeah, that's enough of that. Let's talk about the thing you're here for. We all have an idea of what Kafka is now. So this is what I wanted to achieve, but how do I actually bring this together? Okay. The first thing I needed to do was focus on that metadata that I talked about, that little bit of extra information that I needed to make sense of those readings. This involved a bit of research on my part because every houseplant is different. If you don't believe me, okay, just believe me, all right? They're all different. So I had to do some research, figure out what moisture levels these plants are comfortable with, and I needed to get that into Kafka somehow. Next, I'd focus on building the physical system with that Raspberry Pi and the soil moisture sensors. I'd use a Python script to, every 30 seconds or so, go and capture the soil moisture readings and produce those into Kafka as well. When the data is both those data sets are in Kafka, then I can start doing stream processing. And for this step, I decided to use ksqlDB to do that and figure out which plants actually needed to be watered. And then from there, the results are in Kafka. I need to get them out of Kafka. So I was going to use Kafka Connect to connect my Kafka cluster, that information, to my phone using a sync connector and the Telegram messaging app. Sounds pretty good. All right. First up, hardware. This is not a hardware conference, so we're going to glaze over this, right? But I want everyone to have the tools they need. If you want to build this sort of thing at home, this is what you need. Look at those nice photos. Look at that. A quick aside on the sensors that I chose. I chose some Stemma I2C capacitive soil moisture sensors, which is great. I think they're really high quality. They do what they need to do. They're pretty cheap. I bought like 1 million of them because it was like $1 each is great. The problem is that they're I2C components. And if any of you have dealt with that before, you know that I2C components communicate using a unique address, okay? And that's set at the component level. All of the sensors are then connected to the breadboard up there, and then they all communicate over the same input wires into the Raspberry Pi. Okay, so they need that unique address in order for me to actually pull the correct data from the sensors. The problem is that these sensors had an actual physical limitation in that they could only have a unique address of 1 of 4 values. Wonderful, that's what you get for buying the cheap ones. Anyway, it's great if you only have 4 plants, right? It's wonderful. So for this system, there are ways to get around that, either from the software side of things and hardware, but I was like, it's not worth it right now. So watch this space, maybe it'll get even better. But really going into this, you should know I could only monitor 4 plants at a time. It gets cool, I promise. This isn't actually a disappointment. From the software side of things, also pretty straightforward, Python and the Confluent Kafka Python library. It's also important that I needed a Kafka cluster, right? And so in this case, I'm taking advantage of Confluent Cloud to have a fully managed Kafka cluster. I thought it was a pretty good option to use for this because this is my first hardware project, did I say that? And I didn't want to focus on infrastructure. I wanted to focus on the actual thing I was building. So let's just throw it all in the cloud, right? Forget about it. And also there were a lot of cool tools that I got on top of that, schema registry, managed connectors, and in-browser stream processing. So it all seemed pretty good to me. If you are following along and you want to build this yourself, just know that you need a Kafka cluster running somewhere. Do what you want. All right. As a quick aside, okay, let's get into the actual data we're dealing with. Kicking this off. Again, a takeaway, please. Any project that you're working on that has any data, which is every project, I'm sure, just take a little bit of time, 5 minutes, that's all I'm asking, a little bit of time in the beginning to think about the data you're going to be using. So many problems in software engineering, I think, arise because no one really thought through what data sets they were using, and a field changed, or you can't actually get it, and whatever. And there's a lot of problems. Just think about your data, okay? I promise. It's really easy when you are working on a project for yourself to kind of ignore it. It's like, I'm the stakeholder. It doesn't matter, right? But please, it saves you some time. Schemas are a really, really great way for, to make sure that downstream systems are receiving the information that they expect to receive. And it also helps you reason about the project ahead of time, right? I sat down for maybe 15 minutes max, and I had a whole list of like 3 dozen fields I thought I would need and whittled it down to 10, okay? It's just, think about it a little bit. So that said, I defined 2 Avro schemas, one for the readings that were being captured by the Raspberry Pi, and also for the plant metadata. So for the readings, we had the % moisture. I also got temperature for free from the sensors. I had no plan for that yet, but I figured I'd throw it in there just in case. And then for the plant metadata, this is the stuff I had to do research on, all right? So we needed the low and high moisture thresholds, some details on the temperatures, and also all of their names. There are many: given name, scientific name, common name. So good. And then we also have a plant ID. That's something I just made up, threw in there. This is going to keep track of every plant, serve as the key for the Kafka topics, and help with joining and processing later on. All right. We've thought about our data. Let's actually write some data, right? How do we get data into Kafka? There are 2 main ways. We've got the Producer API and Kafka Connect. I know I have verses in there. I'm a confrontational person, so I like to just do that. But really, there are reasons why you would want to use one or the other. It's not really a competition, or is it? Let's look at that a little bit. Producer API. This is your low-level vanilla option for getting data into Kafka. It's great. It's available in pretty much every language you would want to use for Kafka. You'll want to use the Producer API when you either own the application that's producing the data or you have access to it, right? So if I wanted to say, I have this huge application, I want to capture like a very specific sort of log event and produce it into Kafka. Just 2 lines, add a producer, capture that event as it occurs, produce into Kafka. Great. The other option is Kafka Connect, and as the name implies, it's a way to connect external data sources and sinks with Kafka, okay? It's really great because it's configuration driven. You don't have to actually write any code to make it work. You point to, in the case of a data source, you point to maybe the database, give it a connection string, start it up, and it's going to be capturing information from the database and translating it into events for you to then use within the Kafka ecosystem. It's generally a good option to consider, like I said, if you're dealing with data in a database or data in other sources at rest, like at the end of an API call. And there are a ton of Kafka connectors out there. I think it's like 200 now for different data sources and sinks. So your data, whatever you're storing it in, probably exists, and you can point to it really easily with Kafka Connect. So what did I use for my case? Just the Producer API in this one. You're probably saying, oh, metadata, that should be in a database. Yeah, I don't disagree. But I only had 4 lines of metadata to write in the beginning, right? I only had 4 plants to monitor. So that wasn't worth spinning up a database. So I ended up just using the Producer API. I created a script to take the metadata, serialize it according to the schema that I defined, and produce it into Kafka. From the reading side of things, again, I used the Producer API. I defined an in-script mapping of sensor ID to the plant that it was actually monitoring, and then just kind of looped over that and collected the moisture and temperature readings at 30-second intervals. And here is one of the soil sensors. Another fun thing is that I decided to cut and crimp all of my own wires. Are you proud of me? I'm pretty proud of me. I will never do that again. All right, so the data is being produced. It's in Kafka. Now what? We're basically done. It's easy from here. To process it, you have a lot of options, all right? The OG way is to use the Producer and Consumer API. Again, low-level vanilla option, available in all your favorite languages and all of your least favorite. But to use the Consumer and Producer API for stream processing, there's a lot of steps you got to go through, right? You have to define a consumer, read the data out of Kafka. And if you're doing stateless transformations, great, just do it, produce it back to Kafka, wonderful. But when it gets stateful, that's the problem, right? How many instances of that application are you running? What are you doing in the event of a failure? What if one instance goes down? I don't know, there's a lot of questions. Are you storing state somewhere? Where are you putting it? Why? Does it matter if you have a state? Do we care? Is it that sort of use case? So many more questions, it's almost not worth it, right? So There are some benefits of using the producer and consumer API for stream processing. Again, lowest level options, you're a little more flexible in what you can do with the code at that level. But if you're saying you're going to use one of the next two. So Kafka Streams, this is a Java and Scala library for stream processing, right? It is adept at this, okay? It wants you to do stateful processing, okay? It's really good. It gives you a lot of stateful transformations out of the box, some of them listed there. The cool thing is that it takes advantage of the fact that consumers want to share the work. They want to parallelize the processing. So you define what your input topics are for your Kafka Streams application. You can spin up multiple instances, and as long as there are enough partitions in that input topic, it is going to dole those partitions out across the available instances and parallelize that processing for you. Amazing. And then if one of them goes down, it's again going to use that consumer group protocol to redistribute those input partitions to the other remaining instances and also take the state with it. Okay? So you don't have to worry about where the state goes, where it's being backed. It is being stored durably in Kafka as well. So Kafka Streams is great, way better than the consumer and producer API usually. And then finally, the easiest way to do stream processing in Kafka is with ksqlDB. It is a SQL wrapper around Kafka Streams, effectively. All right, so when you write up a couple SQL statements, it is going to spin up a Kafka Streams application for you under the hood, and you don't really need to think about all the boilerplate code. It's pretty great. And the cool thing is that you can do this within Confluent Cloud, so I don't even have to run ksql anywhere. It's just there, abstracted away. All right. So let's use ksqlDB. This is the easy part, right? Again, no infrastructure. I just want to not think about it. So to write a ksqlDB application, you first need to get data into it, right? And when you do so, you need to decide how it should be represented within that application, right? There are two major constructs in ksqlDB. There are tables and there are streams. Streams represent unbounded, ongoing streams of events. Tables, on the other hand, just represent the most recent value per key, all right? I'm going to end up using both of them. So let's look at that plant metadata, right? I was writing to that topic, that houseplant metadata topic. I have my 4 rows in there. I want to get it into my ksqlDB application. Again, I'm using a table because tables represent the most recent value per key. And if I ever needed to update something, as I'm guessing and checking and trying to figure out what low moisture threshold is good for that plant, I'm going to be updating that value. And when I do so, I want my stream processing application to leverage that most recent value. I don't care what the low moisture threshold was before. I want to use the most recent one. So we're going to create a table. And this should feel very SQL-y, right? The biggest part of this statement that you should focus on is pointing to the topic that is going to back this table, right? And also defining that value format. Again, we're using an Avro schema, so I'm just going to say it's Avro. And the other cool thing about taking that whole 5 minutes to write that schema in the beginning is that as a consumer, ksqlDB looks at that topic, goes to the schema registry, finds the schema associated with that topic, and then uses that to parse all the fields and their values. Remember, there were like 10 or so fields in this topic. I only have to specify one. I only have to point to what the primary key is going to be. That's it. So I don't have to worry about any typos. So yeah, schemas, do it. Okay. So I can take that SQL and I can run it in the Confluent Cloud ksqlDB editor, and now that topic is going to be brought into my ksqlDB application and represented as a table for me. For the readings data, this is a stream, obviously. Every message is relevant in that topic, right? Everything describes the new state of that plant. So I'm going to use a stream. The create stream statement is pretty similar to the create topic one, or create table one. And again, the perks of using a schema, I only have to point to the topic, specify the value format, and it's going to parse those fields for me. All right, both data sets are input into my ksqlDB application, and now we can start working with them. The first thing is to enrich one data set with the other, right? Because the readings on their own are not good enough without the metadata. And this is going to help me with the processing that we're doing later on. So this is a pretty hefty statement. Most of it's just the fields, but let's focus on that SQL part first. So we're joining 2 data sets. In SQL, we're just doing a join, right? So I'm going to go through, select all the fields that I want from both data sets, and we're conducting a stream to table join. I'm using an inner join specifically. There's no reason why there would be one piece of data in the metadata and not in the readings or vice versa, but I wanted to make sure that every output row had all of the details I needed to do the processing later on. All right, so if I run this query, I'm going to get whatever is currently in the state of the application, it will output it. Cool. But I want to persist it somewhere, so we're going to combine this with the create stream statement. So now when I execute that SQL, whatever it outputs is going to be stored and persisted in another stream within my ksqlDB application, and we're backing it with this Kafka topic that I specified. There's one more detail to consider, though. At the bottom, I've included a phrase called emit changes. So this phrase indicates something called a push query, which means that whatever the result set is from that SQL, we're going to make it an open-ended stream, and every result is going to be output to me. It's not just going to be output to me, it's going to be persisted to that stream. So every time a new reading flows in, we're going to execute this SQL statement, take the result, and we're going to append it to this stream. And it's going to keep doing that until I shut it down, right? This is contrasted with a pull query. This is where I'm pulling a finite result set that reflects the current state of the application. So in this case, I'm just accessing the Houseplants metadata topic, and I'm just selecting a subset of them. So it's going to spit out the 3 rows that apply to this and stop. Okay, the data has been combined. We've enriched them. I have all of the information I need. We can actually start acting on what I wanted to do. And as a reminder, whenever a plant had enough low moisture readings, I wanted to receive an alert on my phone. Right? Pretty simple. There's a lot of questions in there. How often should that happen? How do we determine how often that happens? I've changed this a couple times since I played around with this project. I started building this like a year or so ago. But right now, I am capturing the soil moisture readings every 30 seconds. All right? So with that in mind, if I'm getting a reading every 30 seconds and it's low, I don't want an alert on my phone every 30 seconds. That's just ridiculous. Imagine the data rate. So in the event that I'm out of the house or I'm busy or I'm out of conference, right, I thought it would be good enough to get an alert every 6 hours if the plant needs to be watered. That gives me enough time not to fly home. That gives me enough time to, if I'm in the area, do something about it at the end of the day, or at least yell at my partner to go water the plant. I don't know. So every 6 hours seemed good enough. Another thing I noticed is that the sensors weren't perfect. Surprise, they were only $1. Sometimes I could get false low or false high readings, but the general trend over time was that obviously the plant would dry out, so the moisture decreased. But within a given 6-hour period, I figured, all right, it's probably good enough if I received an hour's worth of low readings at some point in that 6-hour window, right? That probably says, all right, the plant actually needs to be watered. So since I'm taking readings every 30 seconds, that means I should at least get 120 low readings within that 6-hour window before I do something, right? So this query, this little query, achieved exactly what I just said. Okay, let's focus on a few quick details. So we are executing it. There's a select statement, right? We're obviously pulling the fields that we want. I am creating a little message that says, this plant needs to be watered. But some cool things to focus on. So I said I wanted to group these things into 6-hour windows, right? So this is where I'm setting up the query to aggregate over 6-hour non-overlapping windows. So already when an event flows in, we're going to bucket it into the appropriate window. And then within that window, I'm going to count the events where the moisture reading is below that low moisture threshold that I defined in the metadata topic, okay? And when I get at least 120 readings, then I'm going to output a result for this query. And note also that I'm grouping by plant ID, so whenever an event comes in, we're bucketing it by what window it belongs in, and then specifying, bucketing it further into that plant ID. And I don't want to oversimplify this. I mean, I think it's pretty cool that this achieves everything I wanted it to achieve. But it's easy to forget when you're looking at SQL that, under the hood, this is a stream processing application, okay? There's state, there are moving components, there's a lot of things going on here. So I just want to clarify, make sure we all understand. So first of all, when you're windowing and you're conducting an aggregate in ksqlDB, the output is a table. All right, and this kind of makes sense. The output is a table where each row is computed per window per key, okay? And that should make sense because a table shows the most recent value per key, right? Also, as each input record is processed, right, we bucket into that appropriate window, right? Then we further bucket it into its plant ID. If the record makes it through that filter, there is a state associated with that window and that plant ID, okay? And so we're updating that state. We're incrementing a counter there. And then, every reading that breaches that threshold is going to be counted toward that 120. And, if it reaches that, we're going to output a result. You might be asking yourself, because we have having count over 120, what happens when we get to the 121st reading? Am I going to output a result too? Am I just going to get that same problem that I wanted to avoid, where I have a low moisture reading over 120 and we just keep inundating my phone? No. Look at the bottom. Okay. We're not using emit changes. We're using emit final. And as opposed to emit changes, emit final waits until the window has closed before it actually assesses whether or not we should output something. Okay? So for a given 6-hour window per plant ID, if a plant has at least 120 readings, this table will have an output message. So that is exactly what I wanted, no more than one message every 6 hours for each of my plants. Haha, all right. That's great, all right? I have that, I'm producing it to a Kafka topic. All I need to do is get it out of Kafka. And that is a solved problem with Kafka Connect, okay? I wanted those results to be received on my phone. I decided I wanted to use Telegram. It has a really cool chat API that you can create a bot with. You're given an API key, and then when you start communicating with that bot, you can identify the unique conversation ID between you and your bot. And then you can use that and create a really handy endpoint, and then you can just send data to your conversation. That's awesome, because then I could use the HTTP sync connector for Kafka Connect, point to that URL, use the API key, use my conversation ID, and then all that I needed to do was use a little bit of regex to extract the message from the Kafka topic. And every time, Kafka Connect is event-driven, right? Every time a message flows into that alert topic, the connector is going to pick it up and send it to my phone, right? So that's exactly what I wanted to do, and this is the alert that I receive on my phone. It's a little dramatic. It just makes me feel bad for them, right? So yeah, this is what I wanted to do. I get this alert on my phone every time my plants need to be watered. That's fantastic. I've achieved what I wanted to do with this project. But after using it in production, I'm like, man, this is bad. I've got things to do. We have to change this. So for example, one pain point for me was, what if I want to monitor a different plant? I only have 4 moisture sensors. What if I want to switch them around, or, it was kind of a process. First of all, I had to go in, use that script to manually write some data into the plant metadata topic, right? And then I'd have to go into the script on the Raspberry Pi that was collecting the moisture sensor readings and also change that because it had a hard-coded mapping from sensor ID to plant ID. And then I have to move the plant around, right? That's too much. I want this to be better, right? I want it to be elegant or something like that, right? So yeah, let's make this a little more interesting. So rather than manually writing that plant metadata, I figured, it would be really nice to have an interactive application to help make this happen. And since I was already using Telegram to push data to me, I figured, why don't I also write data from Telegram? Okay, let's make the bot better. So very conveniently, there's more to the chat API for Telegram. I'm using that same bot API key. I can basically just write a script that tells the bot how to interact with me when I issue certain messages to it, right? So I could use it to collect the information from me, the plant metadata that I want to write, and then just add a Kafka producer at the end to push that information into Kafka for me. That sounds great. I don't have to use a script. That's wonderful. For any Telegram bot, if you want to do this, it all follows the same process pretty much. You define a high-level conversation handler that just says, how do you start the conversation? What steps should it go through? How does it collect information? And any message handlers that you have for each individual stage. If you're into this sort of thing, it's a finite state machine. It's really fun to put together. I actually enjoyed it. And yeah, so here I'm just laying out the conversation flow, starting with, what plant ID are we adding or updating, and then it's asking for all of those details that I have according to that schema that I wrote. And in the end, it will confirm that information and then commit it to Kafka. And diving into one of the message handlers, here I've already prompted myself for the low moisture threshold. I've got some default values in there as well in case I just want to add it quickly. And I'm storing that information temporarily within the state of this conversation and passing that to the next stage of the conversation. So I fetch the low moisture threshold, I'm going to prompt myself to fill in the high moisture threshold, and then return the new state of the conversation that we should go through. And at the end, once all of the metadata has been collected according to that schema, I can produce it to Kafka. And this is a basic Kafka producer, nothing crazy going on here. I did make my life a little bit easier, extracting out a little bit of the boilerplate code. I defined a few helper functions and classes for the clients and the individual data classes. So you see I have a means for creating a producer that is specifically, serializes according to the Houseplant metadata topic, and a function that also converts the dictionary that I'm collecting into the Houseplant data type for serialization. And from there, the rest of the production is pretty standard. So when the bot is up and running, this is the general flow to update that plant metadata, right? So we go through, tells me what plant I want to update, and collects all the information, confirms it, and it sends it off to Kafka for me. But that's not enough, right? I've solved one problem. I can get the metadata into Kafka, but now I got to deal with how do I update the Raspberry Pi script with the mapping of the sensor ID to this new plant metadata. New schema unlocked, all right. So I decided to put it in Kafka. That makes sense. And again, I don't want a database, that's silly. So I set up a new topic that would only contain the sensor IDs mapped to the plant ID. Okay? So this way I could easily change which plant had which sensor. Right? And of course, I set up another conversation handler in Telegram to help collect this information. So it provides me, in this case, I've got this update sensor mapping command, and then it provides me with a hard-coded list of the sensors that are available. I have them marked on the sensor. And then I can just input whatever plant ID I just created, and it's going to send that mapping off to Kafka. And then the last piece of the puzzle, is to have this updated on the collection script on the Raspberry Pi. Because remember, I had it hard-coded, right? A hard-coded mapping of sensor ID to plant ID, and that's silly. Let's make this more interactive. Let's add a Kafka consumer, so when the script starts up, that consumer is going to consume from that Kafka topic, build up that mapping of 4 sensors to their plant IDs, and then the script can use those as it collects the data from the sensors. A couple things to be aware of, though. The first is that the underlying mapping topic, I define that to be compacted. And what that means is that effectively makes the Kafka topic like a ksqlDB table, in that it's only going to maintain the latest value per key. Okay? And that's just, an implementation detail. I don't actually need to do that. But mostly, I didn't care about what the sensors were mapped to before. I just wanted to maintain that latest value and make it faster at startup, because there will be fewer messages for the consumer to go through in the topic. And also recall that consumers keep track of what they've processed, right? I don't want that here, okay? My Raspberry Pi, I have it restarting every day. I forget the reason. There was a reason. Anyway, so every time this script starts, it makes sense. There was a reason. I have it restarting every day. So every time that consumer starts up, it's lost that mapping. I don't want to persist that mapping somewhere. It's persisted to Kafka. So every time that consumer starts up, I want it to start from 0. So I needed to create a non-committing consumer. I needed to turn off that default that says, this is where I've left off, and instead start from 0. So these are the configuration options that do that. So enable auto commit, I'm turning that off, and then auto offset reset says that if I don't have a bookmark, where do I start? So I'm going to start at the earliest part of the topic. And so every time my script starts up, what happens is the consumer blocks the script from processing until it has achieved a mapping of 4 sensors. All right? And then every time we go through that 30-second loop of collecting readings from the sensors, it's going to check to see if there are any updates. So this is it. It is fully interactive from my phone. I don't have to deal with anything. I don't have to open any program to add data to Kafka. It is just in my phone. It's wonderful. It's an entirely interactive pipeline now. And so I'm pretty proud of that fact. This is a really cool project for me because I actually care about it. And I got to play around with a couple things that I hadn't before, right? I built a hardware project. My friends at TNG this morning were talking about deepfakes, and they said, it's easier to learn technology if it's fun. You actually care about it. So this was very motivating for myself. And I'm glad that you came to follow along with this. And if you care about houseplants enough to, do this like I did, then more power to you. But if you don't care about houseplants, I promise you there are some real takeaways from this. You learned a lot about streaming data pipelines. You saw the different ways that you can get data into Kafka, using the producer API, Kafka Connect. You were introduced to stream processing. You saw the different ways you can do that using the producer and consumer API, Kafka Streams, ksqlDB. And finally, you saw how to get data out of Kafka, also using Kafka Connect and the consumer API. And all that came together to build a fully functioning streaming data pipeline, and I promise you, all of those tools are things that you will need for a streaming data pipeline. Every pipeline has some combination of those. So now you have it. You can do it. You can do it yourself. If you are curious and you want to learn more, you want to do this at home or at your job that you're paid for, whatever. Here's some resources from Confluent, our dev portal. We have a lot of tutorials, courses, more fun projects like this listed online. On the right, I have my link tree, which has a link to the source code and more resources, again, if you're curious. And with that, I will now open it up for questions, if we have time for questions. Nice. All right.
Hi. Hi. Hello.
Hey.
Okay. So the question is, the plant ID that you are using, does it refer to a plant type or a specific plant, like an instance of the plant?
An instance of the plant. I do have a couple duplicate plants, but they are unique because they all have different given names.
Okay.
That's the fun thing. All of my plants have names. They are.
I was thinking
It makes it more fun. It's easier to remember than like Rhaphododora tetrasperma. That's lame. Her name's Guinea. Whatever. Anyway, it's fine.
That's cool. But you could also introduce some kind of metadata keyed by plant type, maybe, and then use foreign keys to join this data to exact plant, right?
Yeah, I definitely could. I would still also have a data set to define like which individual plant, because it's nice that I have the given name that I care about in the alert, because I'm like, oh yeah, Bradley, I know where he is, This is so embarrassing. I'm so sorry that you have to see me like this. Yeah, I could split it out into a separate one. I will probably have to do that when I do extend this. I'm renovating my house right now, so I'm like, how many different Raspberry Pis can I get to just have this full monitoring system everywhere? So it will get out of hand. Absolutely.
Cool. Thank you.
More questions here? Do you have any plans for machine learning, analyzing and seeing trends and?
That is the next phase. Yeah, I think once I've collected enough information, I'm trying to build up a full history and also rotate enough of them out to get more data on enough plants. But yeah, it would be cool to be get an alert saying, sometime in the next day, you should water the plant, right? And be able to anticipate that and see how, honestly, just quantify how bad of a plant parent I am. It'd be kind of nice to see the historic trends. But yeah, that's totally something that I'd love to incorporate.
Hi, I would like to ask you, what is the difference between the retention and the grace period that you were mentioning while you were showing the windowing?
And with the what?
The retention and the grace period. Retention is
yeah.
7 days, or
Yeah.
the grace period is 10.
That's
what
important.
Does that? What is the difference?
It's one of
Or
those things
10
I was
minutes?
kind of, yeah. So, all right, that is a good question. That comes up a lot. Okay, so this is the tumbling window. We're defining it to be 6 hours in length. The retention period specifies how long are we going to keep the information for this window around, right? I don't need it after 7 days, all right? I'm not going to water the plant at that point. The grace period says how long are we going to keep the window open waiting for late events. There's a default I think they've changed the API now, so they want you to put one in, and I think the default was like 60 seconds or something. But I don't really have late arriving data because all the information is being collected at the same time, so that really doesn't matter. It's just kind of in there to be in there. But that is a good question. There are use cases where this actually matters. That says, don't close the window until the 6 hours are up, but then also give it 10 more minutes just in case, and then close and output the result.
Yeah. Thank you.
Mm-hmm.
How did you hide the cables from your sensors to the Raspberry Pi?
How did I hide them?
Yeah. So you don't have a lot of cables in your windowsills? And
Well, I've only got like 4.
yeah.
4 cables. That was another reason to not do all 40 plants. It's just unreasonable. Yeah, so they were about this long, each of the cables, and that was almost too short in some cases. All the plants that I was monitoring are on one table, so that made it easy, and there's an outlet behind it, so I just kind of leave that there. It doesn't look very nice. It does not. Right now, I am exploring options to have that part be, the actual sensor be wireless, and sending it over to the Raspberry Pi and then producing that back to Kafka. That's like phase 5, though, because that would be cool, because then I wouldn't have to have any wires, and I could have many plants hooked up to this thing. But yeah, the wires don't look too good. Also, if you look closely, like the soldering isn't that great either. Or do you say solder here? Solder? I don't know. I feel like it's different everywhere. But yeah, for my first project, it looks pretty good. It looks a little remotely professional. Yeah.
Excellent. Thank you very much.
Yeah, thank you. And wait, I have to, this is a Kafka thing before you go. Sorry, it's a streaming selfie. I have to. Thank you. All right, cool. I'll see you all around if you have any more questions, and I also have some small Kafka swag. I've got stickers and pins if anyone is interested, so see me out in the hallway.